So that's the energy inside of the equation in terms of energy reaching the Earth. What about the distance between the Sun and the Earth? You might well imagine if you get closer to the Sun, you'll get more energy, and if you get farther away from the Sun, you'll have less energy. And so we need to look at the Earth's orbit around the Sun. Well, we know the distance from the Earth to the Sun very precisely, to about a meter. It's 1.495978707 times 10 to the 8th kilometers, or as you may have learned it, 93 million miles. Again, that sets a number of the fraction of the Sun's energy that we collect, but the question, as always, is, does it change with time? And the answer is yes, because the Earth's orbit is an ellipse, not a circle, but a squished circle, and the Sun is not at the center of that squished circle, but it's off to one side, what we call the focus of the ellipse. As a consequence, as the Earth goes around the Sun once every year, it alternatively goes closer to the Sun and then farther from the Sun 6 months later and back to closer again at the end of the year. Now, if I showed you this diagram and asked you, where do you think the 4th of July is? The usual answer is on the right, when the Earth is closest to the Sun, because that's when it's going to be collecting more energy. But in fact, that's January 3rd. The 4th of July is when we're at the farthest distance between the Earth and the Sun. Now, that doesn't concord with my experience at all. In fact, that's because the seasons are not caused by this small change in distance between the Earth and the Sun. The seasons are caused by the tilt of the Earth's axis. So on January 3rd, the Earth is tilted away in the northern hemisphere from the Sun. So therefore, the Sun comes in at a more glancing angle, less energy is received for each square meter of ground, and the temperature in the northern hemisphere is colder. Of course, as anyone who's been to the southern hemisphere knows, their seasons are reversed. And in Australia, at Christmas time, it's the warmest time of the year because they are tilted towards the Sun and they're receiving the most energy per square meter. 6 months later, as the Earth goes around the Sun, the angle stays the same, and now the Earth is pointing toward the Sun in the northern hemisphere, making it summer, away from the Sun in the southern hemisphere, making it winter. Now again, the question is, what happens? Does this change? And the answer is yes, because the Earth is spinning, right? Once per day as it goes in its 365-day orbit around the Sun, it's spinning. So it's spinning like a top. And if you've ever spun a top, you know what a top does? It spins like this, and then it starts to wobble like this. That's called precession, as it responds to the torque of gravity attempting to knock the top over. Well, the Earth, of course, is in free space, but it feels the force of gravity of the Moon, and of Venus, and of Mars, and of Jupiter, and of the Sun, so it's constantly being tugged around by the force of gravity, and that induces a precession of the Earth's axis. Such that, while we start out here today, January 3rd being closest to the Sun and July 4th being farthest away, we'll find in about 10,000 years that the situation will reverse and will be closest to the Sun on July 4th in the northern hemisphere and farthest from the Sun on January 3rd. That's going to change things. And there's one other thing I didn't tell you, and that is when we're closer to the Sun, we feel a stronger gravitational force, and as a consequence, we move faster in our orbit. Today, January 3rd is in the middle of winter, and winter is shorter than summer. How do I know? Well, February 28th with only 28 days is in the winter, and July and August with 31 days each is in the summer. Our summer season between June 21st and September 21st is 4 days longer than our winter season from December 21st to March 21st. However, in 10,000 years, this situation will be reversed. And so we will have shorter but hotter summers, hotter because we're tilted towards the Sun when we're closest to the Sun, but shorter because we're moving fastest in the orbit because we're closest to the Sun. Whereas on January 3rd, we'll have longer and colder winters because we're farthest from the Sun, we're tilted away from the Sun, and we're moving most slowly in our orbit. And it turns out the latter is more important than the former. And then, as the cycle continues, we'll come back to where we are today, such that January 3rd is when we're closest and July 4th is when we're farthest. So one cycle takes 23,000 years. Then there's the tilt of the Earth's axis. Now you might say, well, you were just talking about the tilt of the Earth's axis, but now I'm talking about the amount of tilt, not which direction it's pointing in the sky. How much is the Earth's axis tilted over? Well, we know today Exactly what that tilt is 23.43 degrees from a perfectly straight North Pole, and it's pointed at what we call the North Star, Polaris. But Polaris was not always the North Star. Polaris was not where the Earth's northern axis pointed. We know this from ancient structures like the pyramids in Egypt, which are aligned with a different set of stars because 4,500 years ago, this axis had precessed and was pointing at a different set of stars. In fact, the amount of tilt goes over and back to a greater tilt and a lesser tilt. The smallest tilt we have is 22.1 degrees. Today we're at 23.5 degrees, sort of halfway in the between, and the maximum tilt is about 24.5 degrees. So lesser tilts mean weaker seasons, greater tilts means stronger seasons. And to go from here over and back, that takes 41,000 years. Finally, there's the shape of the Earth's orbit, that is, how squished is it from a perfect circle. We call that the eccentricity. A perfect circle has an eccentricity of 0. A squished ellipse has an eccentricity bigger than 0. Today, our orbit is about 1.7%, 0.017, out of being a perfect circle. But it ranges from considerably less than that, 0.005, or only 0.5% out of round, and you can't distinguish that from a perfect circle, to almost 6%, 0.058, out of round, which means the extremities of moving far from the sun and closer to the sun are exaggerated. So the Earth's orbit goes from almost a perfect circle to a squished ellipse, back to a perfect circle again, and that cycle takes about 100,000 years. So here they all are together on a single plot, going from 200,000 years in the past to 100,000 years into the future. You might say, well, how can you predict 100,000 years into the future? It's just gravity. It's just the forces that the sun and Venus and the moon and Mars and Jupiter exert on the Earth, and we can calculate these with exquisite precision. And so we indeed know what these cycles look like in the past, and we can predict what they'll look like in the future. You see at the top, the precession cycle, 23,000 years. Next is the axis tilt over and back, 41,000 years. And finally, at the bottom, the eccentricity cycle, which squished to a circle, back to squished again. You can see at the 0 point, which represents today, we're at one extreme of the 23,000-year precession cycle. We're halfway between the extreme tilts, and we're moving down towards a relatively circular orbit around the sun. Now, all three of these changes are completely beyond our control. We cannot decide to remove Jupiter from the solar system because it messes with our planet's orbit. It's not going to happen. Furthermore, it turns out all three of these have major impacts on the Earth's climate, as we'll see a little later. But, taking them all into account, it is clear, given their timescales of tens to hundreds of thousands of years, that none of them is relevant to the rapid global warming that we're experiencing today on a timescale of mere decades.